Okay, hello everyone. Welcome to class 10. So, we will continue upon the aspects of symmetry, and today we should be able to start what crystal structures are and how that is related to the symmetry operations that we have seen so far. But before that, so last class I have sort of ended by saying that if I have a 3 bar symmetry, the corresponding polyhedron that I am trying to look for is an octahedron, or vice versa if there is an octahedron like this, right. So, one triangle pointing above the plane, the other triangle pointing below the plane with similar sort of environment at all the corners. Then I am going to say that the point which is the center of this octahedron has a 3 bar symmetry. Okay. Similarly, if I have a 4 bar symmetry, I said the polyhedron of interest for us, I mean we have to look for polyhedra which are like tetrahedra. So, again 4 bar is so the easiest way to draw a tetrahedron is this. So, I have a line above the plane, I have a line below the plane, and I join all the corners, I get a tetrahedron, right. So, that is a tetrahedron. If you can imagine properly, you can see a tetrahedron there, right. And so if you populate them with objects of identical objects, then what I have is the corners of this tetrahedron are occupied by identical objects. So, what I have is that the center of this tetrahedron has a 4 bar axis of symmetry, right. Sorry, 4 bar point of symmetry, not axis of symmetry, but 4 bar point of symmetry. Similarly, 3 bar, I have a 3 bar point of symmetry. Okay. Now, so conversely, if I see point symmetry operations which are of 4 bar type, I imagine that there is some sort of underlying tetrahedron in the system which are all connected to each other in some way, and then there is lattice and in a periodic fashion. Okay. Okay, and 6 bar symmetry, we said the 3D object of interest or the polyhedron of interest is actually our prism. Right. So, where both the triangles are in the same orientation. Okay. So, this is okay. So, now maybe can we have examples from real material systems that show 4 bar or 6 bar symmetry, right, before even we go to space groups and point groups, where we will see a lot of materials with certain point groups and certain space groups in them, material systems. But so to give you a very simple example, so nowadays so these 2D materials are becoming very famous. 2D materials are materials which are typically so single sheet of some material that can be exfoliated. So, for example, graphene is a 2D material. So, I can exfoliate it as a single sheet, and this single sheet is technically called a 2D material. So, there is translational symmetry in the plane. So, it is technically 2D, which means along 3D there are no atoms, right. So, along the third direction it's bounded along the third dimension, or the material is just along the 2 dimensions, right. So, graphene you can just draw bunch of hexagons in 2 dimensions and you get okay. So, let me draw it properly again, just like I did it last time. A sheet of this, right. So, that is nothing but your graphene. Okay. Now, why can you make sheets of such materials? Because I mean in general graphene can be made from graphite, and graphite is nothing but such sheets which are ordered on the top of each other. So, this is a graphene sheet. This is also a graphene sheet, right. So, graphene sheets are piled up on the top of each other, and then this is the bulk structure of what is called graphite. Graphite is a mineral that is available in nature, and you can take graphite and peel off layers using the so called Scotch tape technique, right. So, which actually earned a Nobel Prize to exfoliate layers of graphene, and this thing has a Nobel Prize, right. So, but so 2D materials do not stop with and so you call it 2D material in the sense that if you have a sheet, a 2D sheet, it is a 2D material. However, so even when you go in the bulk form, right. So, graphite for example has so the interlayer bonding between these 2D materials is nothing but its van der Waals bonding, right. So, now you may recognize that so graphite so these carbon atoms, so this is all hexagons of carbon, right, and so on and so forth. So, each carbon in plane is bonded to 3 other carbons, right, so at an angle of 120 degrees with respect to each other, right. Now, I mean, so this is one carbon, this is another carbon, another carbon, another carbon, right. So, one carbon has 3 bonds, right. So, but ideally so what is the electronic configuration of carbon? Electronic configuration of carbon has 3 p electrons and sorry I have 2 s electrons and 2 p electrons, right. So, S2p2 system, okay. So, that is carbon. But so when carbon has to bond to other carbons, carbon sort of all these orbitals sort of hybridize and become orbitals of similar energies, degenerate orbitals. So, in graphite, right, so or in graphene or in graphite to a certain extent. So, let us talk about graphite first. Okay. So, this s orbital mixes or hybridizes with 2 p orbitals, creating what are called 3 sp2 orbitals, right. So, these are sp2 orbitals, each of them has 1 electron, okay, and you have another p orbital which does not hybridize, which does not participate in this hybridization. This p orbital has energy, different energy, right, which has another electron, right. So, now this carbon, one carbon can form 3 bonds by 3 what are called sigma bonds. This is all 10th standard chemistry. One carbon can form 3 sigma bonds with 3 other carbon atoms, right. So, those are these bonds essentially. So, I have one carbon, I have a sigma bond, I have another sigma bond, I have another sigma bond. These sigma bonds are stronger bonds, but the nature of this orbital is that it is an sp2 hybridized orbital, right. I am not going to go into details of what is an orbital etc., because this is basic. I mean, so you can just understand this from your 10th standard chemistry, or if you want to understand what orbital really means, you have to take a course on quantum chemistry. Okay. But so I am just going to assume that you have done these things in your 10th standard, right. So, I have an sp2 hybridized carbon orbitals, orbitals which are trying to bond with other carbons. Okay. However, what is remaining is a p orbital, and this p orbital. So, these sp2 hybridized orbitals are in plane, right. So, they are all these are all planar bonds, right. As a result, one carbon can bond with 3 other carbons, but similarly this carbon can bond with 3 other carbons, this carbon can bond with 3 other carbons, and so on and so forth, and it is just going to make a planar sheet, right. However, there is another orbital that still has 1 electron, and that is also itching to bond with something else, and that is your p orbital, and this p orbital is maybe the way I am drawing it is not very good. Okay, you have a planar sheet here, but The p orbital, however, so that comes out of plane, right. So there is a p orbital. I will try to draw something which looks out of plane. I am trying to imagine in which orientation does it look. How should I look at that out of plane, but so probably I am very bad at this. But yeah, so just imagine that there is another p orbital that should just come out of plane, something like that, right. So there is some sort of a pi electron. These are the electrons in this p orbitals are what are called pi electrons, right. These pi electrons, then what they do is they bond between two different layers. So I have one planar sheet of carbon. This is one planar sheet of carbon. If I look at the cross section, this is a second planar sheet, and the bonding between these two planes is because of pi electrons or your p orbitals. It is weak bonding, right. It is also, you can argue that this is actually dipole-dipole interaction, that is a physical bond, or these bonds are what are called van der Waals bonds, right. So you have a 3-dimensional solid, right, where in 2 dimensions the bonding is strong, these are sigma bonds, right, so of carbon, but in the 3rd dimension the bonding is weak, and these are van der Waals bonds, right. So because these are van der Waals bonds, so I can the bonding is not that strong, I can easily exfoliate them. I can put a scotch tape and exfoliate each layer by layer I can exfoliate, sort of, right. And this is the entire this has elicited a lot of interest, and nowadays so you can see that 2D materials are everywhere, including in transistors, and so the next generation of transistors called the nano sheets are going to be made out of 2D materials. 2D materials are making their mark in all different fields, okay. So they are something, a force to reckon with. Now one of the famous 2D materials, a semiconducting 2D material, graphene is a metal, right, because it has this pi electron cloud which delocalizes and forms an electron cloud that conducts, right. But you have other 2D materials. Graphene is not the only sort of 2D material, or graphite, in other words, is not the only material with van der Waals bonds through which a 2D graphene can be exfoliated, right. So the other 2D material, the other famous 2D material is what is called MOS2, or molybdenum disulfide. Now MOS2 exists in two major, so it has many polymorphs, but a couple of important polymorphs, right, so are what are called 2H phase. There is some sort of hexagonality here, and a 1T phase, T meaning trigonal. We will look at what this hexagonal and trigonal are very soon. Now what is the difference between these two, right. So how does MOS2 look like? Now MOS2 is not a single layer of carbon, right, but you have molybdenum, right, which is bonded to 6 sulfur atoms, right. So 3 on the top, 3 on the bottom, okay. So now I have so I have again there is another molybdenum and so on and so forth. So it is a lattice, but I am just going to talk about one unit of this lattice, right. So in this one unit of the lattice, okay, so I am going to talk about one layer of MOS2 is actually one layer of molybdenum, one layer of sulfur on the top, and another layer of sulfur on the bottom, right. And then you have van der Waals gap, and again the same thing starts. You have molybdenum again, let me draw it properly. Okay. So one layer of molybdenum, one layer of sulfur on the top, one layer of sulfur on the bottom. This is one monolayer of molybdenum sulfide. Now if I take molybdenum sulfide in bulk, I do not have monolayer, I have multi-layers, but these multi-layers are again I have S, MOS, but so they are separated by again van der Waals gaps, right. So, I can just do a stacking of molybdenum sulphide. I have sulphur, I have molybdenum, I have sulphur. These are all strongly covalently bonded, the molybdenum and sulphurs. So, it is actually a 3 layer compound, technically speaking 3 atomic layer compound, although we just call it as one monolayer of molybdenum sulphide, right. And then so again the second layer starts, there is MO, there is S, the third layer starts S, MO, S and so on and so forth, right. So, this is molybdenum sulphide. Again you can peel it off, you can exfoliate and you can make a single monolayer molybdenum sulphide, right. Now, how does a single monolayer look like? A single monolayer has again a molybdenum, so the plane of molybdenum atoms. Each molybdenum atom is bonded to 6 sulphurs, right. So, there are 3 sulphurs on the top. So, sulphur will be in red color, right. So, there are 3 sulphurs on the top. So, one forming a triangle, right. So, the third sulphur is somewhere here, it is out of plane, it is coming out of plane, these two are going in the plane. So, this is minus minus, this is plus, right, and you have 3 sulphurs on the bottom. Again if this is plus, if this is minus, this is plus and this is minus again, right. So, essentially I have a prism here, right. So, I have a molybdenum and I have one triangle, I have another triangle, right. So, with respect to the molybdenum position, right. So, I have a 6 bar symmetry in this structure. Now, this structure with a 6 bar symmetry is 6 bar point group symmetry it is called, but yeah, point symmetry is what is called a 2H structure of molybdenum sulphide. Okay. So, this is sulphur, 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 sulphur. Now, other molybdenum atoms keep the symmetry. It is the symmetry is not just confined to this point, but all the other lattice points of molybdenum have a 6 bar point group symmetry that is about these points. Okay. Okay, that is the 2H phase of molybdenum. However, I have molybdenum here. Sorry, what was the color of molybdenum earlier? The color of molybdenum was okay. So, I am just mixing up everything. So, that is okay. So, let us do it carefully here. So, let me use the color of molybdenum as this one. So, this is molybdenum and here I have sulphur atoms, 2 of them going into the plane and 1 of them coming out of the plane, right. So, I am just going to put it slightly below, giving a 3-dimensional view of a triangle for it. Now, instead of actually reproducing the same triangle verbatim, in the bottom layer I am going to put this out of plane, sorry, this into the plane, this atom into the plane and this atom out of plane, and I have rotated the entire thing by 120 degrees, sorry, by 60 degrees or 180 degrees. Okay. So, essentially what I have if I turn it is so instead of having a biprism, a trigonal prism, what I have is an octahedron. So, I will have a configuration like this. This is molybdenum, right, and then so molybdenum is at the center, but sorry, so these are rotated with respect to each other. Okay. So, what I have here is an octahedron, or what I have is this is molybdenum, and with respect to molybdenum this is coming out, this is going in, right, this is coming out, this is going in, this is coming out, sorry, this is in, out, out, right, and also a rotation by 180 degrees, right. So, as a result you get something like there is a back triangle which is in red, there is a front triangle which is in blue, and there is a molybdenum in between, right. So, with 6 sulphur atoms, right. which is bonded to 6 sulfur atoms. So, what is this? This is a 3 bar symmetry, or what I have here is an octahedron. Okay. Very simple, right. So, if I have a 3 bar symmetry, and in fact you can see from the space group of this will be something like P 3 bar, I forget what exactly the space group of molybdenum sulfide is, but there is a there is a point group which is 3 bar about a certain axis, and which means there is a point operation which is 3 bar about a certain axis, and P 3 bar m or P 3 1 or something like that, right. So, I do not exactly remember the space group, but yeah, so molybdenum sulfide in its 2T phase has a different symmetry. Now, molybdenum sulfide in in 1T phase, it is not called 2T, it is called 1T phase. Molybdenum sulfide in 2H phase has completely different properties. Let me put it as optical properties than molybdenum sulfide in 1T phase, and 2T you can try and convert 2T into 2H into 1T or vice versa through some materials engineering strategies, but that conversion, that phase transition is akin to changing the symmetry, right. So, the phase transition is akin to changing the symmetry. Atomic arrangements of changing the symmetry, right. So, from 6 bar to 3 bar or vice versa. Okay. So, at a point symmetry level, right. So, we are actually going to see that the entire space group changes when you change phases, right. So, when we talk about space groups, that is okay. So, that is one example of where you so you can find this octahedra, and so the octahedra are sort of transforming into prisms when you have a 1T to 2H transition, and vice versa the prisms are sort of transitioning to octahedra, and so on and so forth. Okay. Now, you can as well think about so the more common examples are metals, right. Now, metals, FCC metals, right. I'll explain what an octahedral void is using what is the octahedral position in an FCC metal. So, the way one can think of so if I am putting atoms on the top of each other, right. So, I am going to stack atoms along the C direction, right. Okay. So, first layer of atoms are these, I always do not draw it well, but first layer of atoms are again. So, I am talking about atoms here, right. So, I am so I am jumping some guns and talking about atoms just to explain you what these octahedral positions are, right. So, these atoms are all closely packed, right, and so on. Hang on. So, these are the first layer of atoms, right. So, they keep they slide from each other by 1/3 the lattice parameter, but these are the first layer of atoms, right. Then on the top I put, so now let me just join it before it becomes difficult to observe what I am saying. So, I am joining it with a green triangle. Okay. So, on the top of this green triangle, right, I am going to put another layer of atoms which are in a different color, right. So, it is going to be something like this. Right. If you see that center position, that is still left alone. Okay. Now, this is my red triangle, right. So, this is how FCC metals stack up, the atoms of the FCC metals start stacking up on the top of each other. So, what you have there, the center of this, so I have a red triangle, atoms on the red triangle, which is layer 2, and I have atoms in the green triangle, which is layer 1, which are on the top of each other, right. So, at the center of these two there does not need to be an atom, right, but there is a point there, right, about which I have a 3 bar symmetry. Center of these two triangles I have a point about which I have 3 bar symmetry. Okay. Now, that point in metals is what is called octahedral void, in FCC metals is what is called an octahedral void. Right. Similarly, you can define what are called tetrahedral voids and so on and so forth, but yeah. So, this is a position which is called an octahedral void, because there is an octahedron and there is a void there, right. So, if you want to put in some interstitial atoms, you can put them in those voids, right. So, and so on. Okay. So, these octahedra and tetrahedra and these prisms, these sort of shapes keep coming, right. So, at a very basic level, at a very modular level of or a molecular level, right. So, you see that the entire crystal structure is made of such octahedra or tetrahedra or some sort of regular polyhedra, okay, in many different crystal systems, right. So, it is important to identify these sort of entities and then infer symmetry from them immediately. If I see octahedra, I am sort of thinking that okay, so perhaps I should in a crystal, if I see that there are some octahedra, I am thinking that okay, so first thing maybe I should actually inquire if this crystal has a 3 bar symmetry about a certain axis, right. Similarly, if I am seeing tetrahedra, I should I think okay, so is there a 4 bar axis of symmetry, or so the environment conspires such that it removes the 4 bar axis of symmetry, right. So, these are my initial thoughts that come in when because from now on I have to see crystals and then understand how symmetric are they. So, what is the symmetry in these crystals, what are the different symmetry elements in these crystals, right. So, that is the exercise that we will be doing. Okay. So, these are a couple of examples for the things that I have been saying, but I am just going to show you very quickly visualization software, and I said that this is what is called Vesta. I asked you to download Vesta so that it becomes easy for you to understand and visualize, right. So, my drawings may not be that accurate, but if I have a 3D visualization software such as this, where I can rotate around and I can see things, right, so then it becomes much easier. So, here for example, you see, so this is MOS2 in its 2H phase. I have downloaded the crystal of MOS2 in its 2H phase, and so I see it in a certain orientation. You see, so I can see there are 6 bonds surrounding every MOS2, as you can see, right. So, this is MO and there are 6 sulfurs, and if I actually see them properly, these 3 are above the plane and these 3 are below the plane, right. And if you orient this nicely and play with this at home, right, you will see that so in a 2H phase they are all oriented on the top of each other. This triangle, for example, sorry, just before this class I was doing this properly, without getting confused. So, or I mean I can reduce the number of atoms, etc. if I so if you can, so you can just play around with the software, and so this triangle of atoms, this atom and sort of, yeah, so this triangle and this triangle are just on the top of each other. So, along a certain orientation, if I look at it along C axis, right. So, there are 2 triangles here which are right exactly overlapping on the top of each other, right. So, that is your 2H phase of MOS2. Similarly, you can do these operations for 1T phase of MOS2 and try to understand what is the structure of MOS2. Okay. So, I will be coming back to this software again later so in about 2 to 3 classes, when I am actually going to talk about real crystals, and I will be showing you different visualizations using this software. But for now I want you to download this software and understand, so the name of the software is Vesta. It is a free software, crystal visualization software. In 3D. Okay. So, and to so first you should put in some crystals into this software, and these crystals are available in several databases. The crystallographic files are available in several databases. One of the databases is what is called COD, right. So, crystallography open database. Okay. And another one which has many more crystals which are even theoretically predicted, not necessarily even experimentally seen, is what is called materials project. Both of them are free. For this you may need an account, a Google account will do, and from these databases you download. So, if I want the crystal structure of MOS2, all the details about the crystal structure of MOS2 are will be present in the softwares. Right, given its space group, the what are called Wyckoff positions, etc., all this we are going to actually talk about in the later part of this class, but all the information about the crystal is given in a file called CIF file, right. So, CIF is what is called crystal information or crystallographic or crystal information file, right. So, you can download the CIF file of any crystal of platinum, molybdenum sulfide, barium titanate, whatever crystal you want, right, to be able to visualize this crystal, and the CIF file can be directly read in the Vesta software. Okay. So, you can just import it onto Vesta and then the visualization comes and you can easily play around with it, right. So, I encourage you to download both Vesta and download certain simple crystals, right. So, you can download some metals such as platinum, right. So, this is FCC, then you can download MOS2 like I said in the 1T phase, 2H phase, play around with it, right. You can download something like barium titanate, you can download something like cerium oxide, right. So, all these crystals and try to understand, just play around for now, and later on when we actually come to proper crystal structures you will understand, oh, what are the different polyhedra here, what are the different point group symmetry operations in this crystal, and so on and so forth. Okay. So, but you can already start downloading and playing with these softwares. Okay. So, that is about the software. Now, let us change gears a bit and talk about. So, I have been telling you something about crystal structure without really defining what crystal structure is. Okay. So, to actually go to crystal structure, so I have been just talking about point symmetry operations so far. So, I have been talking about symmetry, but not the structure, right. So, now let us come to the second part of what I have been writing, symmetry and structure, right. So, the title of every lecture since class I think 7 has been symmetry and structure, or class 8, right. So, let us talk about the structure part. Okay. Now, to understand what a structure is, we start with what a lattice is. So, what is lattice? Lattice is a periodic arrangement of some points, right. So, for example, if I have so something like I can just draw a lattice, right. So, I have certain points which are periodically arranged, in this case in 2 dimensions, right. The group of all these points is nothing but it is called a lattice, right. Now, so if I have certain base certain I do not want to confuse you by using the word basis, but if I have certain coordinate system in which this lattice can be represented. So, I have A, B and C, right. So, certain C is somewhere coming out of plane, right. So, A, B, C are non-coplanar, vectors and none of A, B, B, C or C, A are also non-collinear, right. So, they are all independent vectors, right. So, they are not dependent on each other, right. So, non-collinear vectors. Then you can use A, B, C as a coordinate system. So, this is my coordinate system. In this coordinate system, any lattice point is given as u a plus v b plus c w, the other way around, w c. So, this is any lattice point. Okay. I am not yet imposing the condition that u v w should be integers, because we are going to talk about what are called Bravais lattices, where u v w need not be integers, right. So, but this is any lattice point which is integer or some sort of a fraction, a rational number, right. But this is a lattice point, and I am so the lattice point I am just going to get rid of the coordinate system and just going to represent it as u v w. Okay. Now, the entire lattice, however, mathematically is nothing but a combination of, so wherever there is a lattice point is at u v w, u plus a, or there is some sort of translational periodicity in this lattice. So I am just going to write it as a combination of, so there is a delta function, a point function is nothing but a delta function, right. So, there is infinite intensity at this point and there is 0 intensity if you go away from that point, right. So I am just going to write it as a summation of various delta functions, where delta function is infinite at at a lattice point, which is r u v w, and elsewhere from the lattice point. So, it is not infinite, I mean it is 0, right. So, delta of r equal to, what is a delta function, equal to is 0 if r not equal to 0, and delta r is infinite if r equal to 0. So, that is a delta function, it is just you have infinite intensity at that point and you move away from the point, you have nothing. So, it essentially a point is a delta function, okay. So, in 3 dimensions. So, the lattice is just a summation of all these points, right. So, all these points which are sort of translational, which have a translational periodicity, right. And a lattice also, I am going to impose the condition from now on that lattice has a translational periodicity. Right, which means that I just said, okay. So, if I start with a lattice point as the origin, right, if 0 0 0 is a lattice point, then any so and a, b, c are your coordinates, then n1 times a plus n2 times b plus n3 times c is a lattice vector, or u times a plus, it is the same thing, plus v times b plus w times c is a lattice vector, right. So, this is saying that there is some periodicity in the lattice. Okay. So, mathematically this is how lattice is defined. Lattice is a set of points, a periodic arrangement of points, and these points are all so mathematically it is a summation of different delta functions. Okay. So, it is an abstract quantity. This point does not need to have an atom or does not need to have any entity that you want to put, it is just a template, right. So, it is a periodic template. Now, on this periodic template we are going to put something and make a crystal structure, right. So, but lattice by itself is just a template, it is just a periodic template. Okay. So, so that is a lattice, and probably so I will stop here in this class by defining what a lattice is. In the next class again we clearly go to what a what a unit cell is first and what a crystal structure is, and we will classify crystal structures essentially into 7 different types of crystal systems, and this classification you may have studied in your other courses as so the classification depends on what is the unit cell of these crystal systems, but I am going to argue and I am going to prove to you that this classification of different crystal systems actually originates from the symmetry that we have studied in the past 2-3 classes, right. So that is where I am going to relate symmetry and structure. From symmetry, from these point symmetry operations come the crystal structure classifications, right. So that is going to be the content of the next class. Thank you very much. I will see you again in the next class. See you. Bye bye.